On the evening of April 15, 2019, the 13th century wooden roof of Notre Dame, known as the Forest, was entirely consumed by fire. Minutes later, the 19th century spire gave way, sending hundreds of tons of burning debris plummeting into the nave. This 3D wireframe shows the sexpartite vault forming a physical separation layer. The outer timber roof shielded weather, while the inner stone vault protected against fire. During the blaze, this mechanism activated. The vaulting shells caught the burning timber, shielding the interior. This floor plan highlights the specific sections of the vault that collapsed. While the interior was saved, losing the roof structure altered the physical forces acting on the 800-year-old stone, leaving the entire cathedral in a state of critical instability. This vector diagram isolates the stone-ribbed vaults. The masonry's sheer weight generates massive outward thrust forces, pushing the upper walls outward. To counter this, 28 massive flying buttresses surround the exterior, pushing back against the walls to create a locked loop of counterpressure. The immense weight of the timber roof originally helped pin the walls down, stabilizing that loop. Without it, the surviving stones were suddenly exposed to unpredictable wind pressures and uneven load stresses. The physical ruins were too fragile to touch. Engineers could not bring in heavy machinery or start stacking raw stone. They first needed a microscopic map of how the heat and collapse had deformed the surviving masonry. To save the physical building, the architects turned to digital simulation. They needed a virtual environment to test forces and simulate loads before moving a single real stone. Years before the fire, historian Andrew Tallon completed a mapping project using advanced laser scanners to record the cathedral's complex geometry. Tallon's equipment captured over 1 billion individual data points, generating a highly precise point cloud model of the entire structure. High-resolution scanning recorded details that traditional surveying tools missed, revealing the original medieval builders' intentional imperfections and subtle design quirks. Tallon's billion-point record provided the only surviving map of the original architecture, functioning as a perfect digital twin for the reconstruction. Engineering teams used this baseline LiDAR data to construct a complete building information model, or BIM. This provided a safe, highly accurate virtual testing ground for the reconstruction effort. The restoration teams did not have to guess how the stones originally fit together. They possessed a flawless mathematical blueprint of the past. The teams then began a digital autopsy, capturing continuous post-fire laser scans of the charred ruins and exposed foundation. This diagram demonstrates how the autopsy worked. By overlaying the new post-fire scans onto the pristine pre-fire model, engineers isolated millimeter-scale anomalies and mapped exactly where the surviving walls had shifted. Scanning deep into the exposed rubble eventually revealed an architectural element that had been completely concealed since the Middle Ages. The intense heat of the fire stripped away centuries of stone and plaster layers, exposing massive iron staples physically binding the cathedral's foundation stones together. Radiocarbon dating confirmed these iron clamps date back to the early 12th century. The data proved that Notre Dame was the first Gothic cathedral in Europe to rely on an iron skeleton for structural stability. The disaster operated as a violent excavation. It forced modern geospatial technology to document ruins that ultimately revealed engineering secrets hidden for 8 centuries. Pushing toward a December 2024 reopening, the physical reconstruction site became an immense logistical operation, operating under a unique paradox. Cutting-edge algorithms and laser grids managed the project logistics, yet the physical labor itself required a strict return to medieval techniques. Recreating the forest required thousands of green oak trees to be felled and manually shaped by carpenters wielding traditional hand axes, matching the tool marks of their 13th century predecessors. The modern data mapped the exact dimensions, while the ancient physical labor executed the cuts. It became a direct collaboration between 12th century craftsmanship and 21st century software. Rebuilders are using the digital model to ensure that as human hands replicate the original structural logic, the AI proves the math of the 12th century design. The digital preservation effort ultimately expanded beyond the physical geometry, capturing the invisible data exposed in the wake of the fire. Scientists are analyzing the charred oak beams recovered from the debris, extracting carbon isotopes that record the specific climate conditions of the High Middle Ages. This heat map shows the results of a field called archaeoacoustics. Researchers are currently working to digitally model and save the historic sound profile of the cathedral itself. Using acoustic measurements taken before the fire, teams are digitally reconstructing exactly how sound rates interacted with the specific geometry and materials of the lost interior space. The Notre Dame experiment has taken a fragile physical building and translated its properties into an indestructible, multi-layered data archive. The master builders of the 12th century laid stones designed to last a millennium. Now, the data scientists of the 21st century have ensured that the cathedral's true engineering, acoustic, and environmental record will survive indefinitely in the digital realm.